Okay, in the previous classes, I have talked about chain maps, right? Between two chain complexes, right? Uh, so today we'll call we'll discuss chain homotopy. Chain homotopy. But first, let us recall what is a chain map. So suppose we have two chain uh, complexes, right? So Q C Q minus 1, C Q minus 2, like this. And we have another chain complex CQ prime, CQ prime minus 1, C prime, Q minus 1 prime, CQ minus 2 prime, and so on, like this. Okay. Then uh, then we have boundary maps, right? Suppose this is Q minus 1, Q minus 2, this is Q prime, this one prime, prime. Okay. So a chain map uh, from this chain to this chain is of course a chain map tau from uh, so tau from this chain complex be denoted by C, this is by C prime. So tau from C to C prime is simply a collection of homomorphisms, right? Uh, right. So this is so this is a homomorphism from chain C to C prime of degree uh, 0, right? Such that, right? So a homomorphism from C to C prime is a collection of homomorphism of this form, right? So this is a homomorphism of degree 0, means tau q is from CQ to CQ prime. Such that it commutes with the boundary map, right? So if you apply this, you apply boundary map this one, then you apply tau q minus 1, right? Then it will go here, right? This is equal to this is equal to you apply first tau q and then q prime. So this. So for every q it satisfies this condition. Or if there is no confusion, we simply write it like tau boundary equal to boundary tau. So it commutes within the boundary map. So here boundary, here this is boundary map on this chain. This is boundary map for this chain, right? So it is understood. So a chain map is a chain homomorphism which commutes with the boundary map. So let us see what is a chain homotopy. Let tau prime from C to C prime be chain maps. A chain homotopy D from tau to tau prime is denoted by this is a homomorphism this from C to C prime, C to C prime of degree 1, such that for all Q, this dq boundary q plus 1 plus dq minus 1 boundary q equal to tau q minus tau q prime from cq to cq prime. Right? So this is, of course, this is a map from this is a homomorphism from here to here. So this is the definition of chain homotopy. So here what you have here, here you have CQ, here you have CQ minus 1, right? Let me just see a picture. So here you have CQ, CQ minus 1, right? And then this is your boundary Q. Then here you have CQ prime, boundary Q prime, CQ minus 1 prime. This is your CQ plus 1 prime, boundary Q plus 1 prime. So DQ, DQ is from CQ to CQ plus 1 prime, right? Because it is of degree 1. So this will be from here to here. So this is DQ. Okay. And then you apply boundary map, this one. Okay. So this compose this plus this, right? Composed dq minus 1. It will be from here to here, right? dq minus 1, right? So this compose this plus this compose this, right? Equal to this, right? You see? So this tau q and tau q prime, they are maps from here to here, right? So these compose these plus these compose these equal to tau q minus tau q prime, right? So both tau q and tau q prime, they are from here to here, right? Now, if there is a chain homotopy from tau to tau prime, we say that tau is chain homotopic to tau prime, and we write so observation chain homotopy is an equivalence relation. Chain homotopy is an equivalence relation. And the class of chain maps. All right. So how we let us see quickly. So suppose we have a collection, this, right? This is collection of chain maps from C to C prime, right? Now suppose we have so what we have to show, so what is the relation here? Tau is related to tau prime if and only if tau is chain homotopic to tau prime. Okay, so first we have to show it is reflexive. So if there is some chain map, right, then tau is related to tau itself, right? How it is? So what we can do, so here what D we choose. So just see that we need to show that this DQ, or quickly if we just do then D boundary plus this equal to tau minus tau, right? So here suitably we can put here we can put dq, here boundary q plus 1 prime, here boundary q, here your q minus 1, dq minus 1. and here tau q minus tau q. So this is 0, of course. If we have tau q minus tau q, so let me put it here, maybe q plus 1. This is q minus 1, q. Okay, and this is q, q. So what d we should choose so that this holds. So you can see that if we choose d to be this, uh, so we can choose. So we want this and d such that this holds, right? Choose d equal to dq, where dq is 0, right? dq is from cq to cq plus 1 prime, but it is 0 mark. We can always have this. So if that happens, then this is dq 0 means this is 0, and then this is 0. So of course, it will be equal to tau q minus tau q, which is itself 0. Next property that we need to show is your uh, symmetry. So tau. So tau 1 uh, tau is related to tau prime, right? Implies tau prime is related to tau. So we have to show that, right? So this so we can choose, implies there is a homotopy, right? From tau to tau prime, right? You choose d prime equal to minus of d, right? So what will happen? Uh, so this your d q prime, because what you want, tau q minus tau q prime, right? Yes. But when you tau prime is related to tau means you have to have tau q prime minus tau q equal to that. We have to have homotopy satisfying that condition. So this on the q plus 1 prime plus minus 1 prime equal to tau q. Right? We just multiply by minus in that inequality, in that equation. So we'll have this. So because we have this, so because let me write that q plus 1 prime dq plus d q minus 1 q is equal to tau q minus tau q prime. Okay, so if you multiply by minus 1, then here minus dq minus dq here minus dq minus 1. So minus dq you put just dq prime minus dq minus prime minus 1. You put my dq prime minus 1. So reflexivity is there. Symmetry is there. So symmetry and reflexivity we have seen. So what about transitivity? Tau is tau prime and tau prime, tau double prime, right? Implies there exists d1 let me d and d prime such that your d q q plus 1 prime plus d q minus 1 q tau q minus tau q prime. Okay, and because d prime is homotopy from here to here, it means what? This is d q prime on the q plus 1 double prime plus d q minus 1 prime q prime equal to tau q prime minus tau q double prime. Okay, now what we can do, we can add these two equations, right? So adding 1 and 2, what we'll get? From 1 and 2, we have so what we are getting if we add, then this will cancel, then tau q minus tau q double prime will be there. But here we need to adjust to get something like, let me use this one. So we want to get what exactly? We want to exactly get tau q minus tau q triple double prime equal to some, we want to get some homotopy that is maybe d double prime, right? So we want here dq on the q plus 1 double prime plus dq minus 1 double prime q this, yes, we want this. So boundary q plus 1, we have this, something we have to probably add and subtract, and then we have this. Okay. So how we are going to get this, and yeah. So dq and dq minus 1 prime. Okay, so if we add, then what we are getting actually, uh, boundary q plus 1 prime. So first let me write exactly what we want. So this is q plus 1 double prime dq prime plus these two terms will write. So q plus 1 prime dq plus dq minus 1 prime and dq prime plus dq minus 1 q equal to tau q minus tau q double prime. Okay, so how are we going to adjust it? No. I think there is some mistake. Here, there is a mistake actually in writing. So this is yes, yeah. So here there is a mistake in the second one. So change this tau prime and tau double prime. They are homotopic chain maps from C to C prime itself. So here this is simply this is just this, not double prime. There is no meaning of that. So boundary q plus 1 dq prime plus this is so this is prime actually, and this. So we have actually this. So yeah, boundary q plus 1 dq. Just a minute. Yeah. So it is this, and we want uh, exactly this. Yeah, we want this, and this q plus 1 boundary q plus 1 prime dq prime plus dq minus 1 prime boundary q uh, minus 1 prime boundary q, not q prime, and then we have this last one dq minus 1 boundary q. So something we should get common now. Here we are going to get common. So, and here we are going to get common boundary q. So this implies your boundary q plus 1 prime dq prime plus dq, and then here we have dq minus 1 prime plus dq minus 1 on dq tau q minus tau q prime double prime. So this thing we can take to be dq double prime, and this one dq minus 1 double prime. So we have a homotopy from tau to tau double prime. So if tau is homotopic to tau prime is homotopic to tau double prime, then tau is homotopic to tau double prime, and homotopy is this d. Homotopy is d, which is nothing but d prime homotopy is d double prime, which is nothing but d plus d prime, right? So this. So we have shown reflexivity, symmetry, and transitivity. It means that this homotopy is an equivalence relation over the chain maps from C to C prime. So this okay. The set of equivalence classes of chain maps from C to C prime is denoted by this symbol C semicolon C prime. This. And if tau from C to C prime is a chain map, then its equivalence class is denoted by this. Next we have a lemma. The composites of chain homotopic chain maps of chain homotopic chain maps is next are homotopic topic. So assume that D is a homotopy from tau to tau prime, where tau tau prime are chain maps from C to C prime, and D bar is a chain homotopy from tau bar to tau bar prime, where tau bar and tau bar prime, they are chain maps from C prime to C double prime. So tau is homotopic to tau prime, and tau bar is homotopic to tau bar prime. So we need to show that tau composed tau bar is homotopic to tau prime composed tau bar prime. Now what we have, because this is a homotopic from here to here, means what? This. So here means we will use short notation actually. So D, this is homotopy, means D composed boundary plus boundary composed D equal to tau minus tau prime, and D bar boundary plus D bar boundary equal to tau bar minus tau bar prime. Okay. Now what we'll do, we will compose this implies so we compose tau bar from left, right? So that is tau bar composed this. We'll do this. So because this equal to this, so tau bar, this composed tau bar equal to this composed tau bar. So what we'll have? Tau bar composed boundary D plus D boundary equal to tau bar composed tau minus tau prime. Okay, and here we compose tau prime from right this equation. So we have boundary D bar plus D bar boundary composed tau prime equal to tau bar minus tau bar prime composed tau prime. Okay. So from 1, so this is two, right? So from 1 what we'll get, so because composition of maps is associated, right? So this, so of course here we are using simpler notation, right? So here suitably we can put here q plus 1, q minus 1 wherever required, right? So this uh, so because of associativity and this tau bar prime and tau prime, they are chain maps. So they will commute with, they are going to commute with boundary maps, right? So this here, for example, from 1 and 2, we have, so this one, this tau bar composed boundary map D, this is going to what? Because tau bar commutes with boundary map, this is nothing but boundary composed tau bar and then compose D, right? So we can write here, so we can write here boundary tau bar compose D plus, similarly, we have here tau bar composed D. So here we don't need to write this composition sign. It is understood, right? So this is boundary tau bar D plus tau bar D boundary plus equal to this tau bar compose tau minus tau bar compose tau prime. And from this one, I see boundary D bar tau prime plus D bar. So this tau prime and this boundary map, it will compute. So we'll have tau D bar tau prime boundary equal to this tau bar this tau bar compose tau prime minus tau bar prime compose tau prime. Okay, now if we add these two, then this and this will cancel. So this is, you can call it, so this is, we can call it 3, call it 4, and this comes because this because a chain map commutes with boundary map. Okay, so from 3 and 4, what we have, we can just add these two. So we have this boundary map tau bar D plus D bar tau prime plus tau D plus D bar tau prime boundary equal to tau bar compose tau minus tau bar prime compose tau prime. So if we put D double bar equal to tau bar D plus D bar tau prime, then clearly this D double bar is a homotopy from tau bar tau to tau bar prime tau prime. Okay, this completes the proof. Okay, okay, we'll stop here.